So hello everyone, today I will be presenting to you my project of Data Science 3 ISO 272 course taught to us by Nigam sir. The topic of our presentation is Know Your Habitat. First, let me introduce you to my group members. Athar Kumar, this is me, Mohit Singh, Krishna Singh, Rajiv Sharma, Gyanesh Ranjan and Nihal Singh. So let's move on to the objective of our project Know Your Habitat is to design a software that basically accepts a media which includes both photos and videos of IT Mandi and then identifies the buildings like academic areas, hostels, sports complex, gymkhana, etc. which are present in that image. So let's move on to the approach which we have followed. The approach we have followed is we are first building a CNN model, which basically includes a data set of images clicked from various places, clicked from various places at different angles of various buildings, and then divided into three classes: North, South, and Mandi. Now the work of a CNN model will be to classify the image, whether the image, the photo has been clicked, photo or video has been clicked from North, South, or Mandi. Then we have moved on and we have changed three models using YOLO, which basically detects the buildings which are present in that image. Now we are using YOLO V4 model to detect our buildings in the image. To use YOLO V4 model, we have first made a custom data set in YOLO V4 format. Then we have customized the configuration data file. Customizing the configuration data file basically means that we are changing the batch size subdivisions, etc. in the configuration file so as to get more precise results. Then we have further we have created two Python files, which one file is basically splits the data into training and testing data, and the next thing and the next file basically converts our annotated data form to proper YOLO V4 format. And after training data, we do the predictions.
Hello everyone, my name is Mohit Singh and I'll be telling about CNN, convolutional neural network. Convolutional neural network is a subset of machine learning. It is one of the various types of artificial neural networks which are used for different application and data types. A CNN is a kind of neural network uh, architecture for deep learning algorithms and is specifically used for image recognition and tasks that involve processing of pixel data. There are other types of neural networks in deep learning as well, but for identifying and recognizing objects, CNNs are the network architecture of choice. There are many reasons that CNN are better than their alternatives in some terms. For example, there is also a neural network called as recurrent neural network RNN. It uses sequential or time series data input and it is suitable for applications involving natural language processing, language translation, speech recognition, image mapping. But the CNN can uncover key information in both time series data and image data. For this reason, it is highly valuable for image data tasks such as image recognition, object classification, and pattern recognition. To identify patterns within an image, CNN leverages principles from linear algebra such as matrix multiplications. CNN can also classify audio and the signal data. So this is why CNN is better than other neural networks when we are considering image recognition. So as our topic was know your habitat, so it is about image recognition. So that's why we decided to use CNN. Coming to the next slide, it tells about the working principle of CNN. See, the CNN convolutional neural networks have many layers. It starts with the convolutional layer, then it goes to the pooling layer, and then the fully connected layer. So as the image, as the in the input we use an image, and it designates weight to the image based on the different objects in the image. So this is the whole process that continues till we are able to decide we are able to decipher that what is the image. So starting from the convolutional layer, which is the first layer or first pathway of CNN. As I told the sequence of work in CNN, that first we'll give an input image, and then we'll have a convolutional layer, then the pooling layer, and then we have a fully connected layer. So in the convolutional layer, a majority of computations happen in the convolutional layer only, which is the core building block of CNN. And there's also second convolutional layer can follow the initial convolutional layer. A second convolutional layer can also follow the initial convolutional layer. The process of convolution involves a kernel or filter inside the layer, moving across the receptive field of the image, checking if a feature is present in the image. Over these multiple iterations, the kernel sweeps over the entire image. After each iteration, a dot product is calculated with the input pixels in the filter. The final output from the series of dots is known as a feature map or convolved feature. Ultimately, the image is converted into numerical values. In this layer, which allows the CNN to interpret. So this was the whole working of the convolutional layer, and after it, the pooling layer comes, and after that, the fully connected layer. Fully connected layer is where the image classification happens in the CNN based on the features extracted in the previous layers. Coming to the
Hello everyone, myself Nihal. I'm going to introduce an important layer of convolutional neural networks called as max pooling. It is a very important layer from the spatial invariance perspective. If we want our CNN model to recognize an object in an image correctly, even if the object has its features tilted, distorted, different light compositions, textures, etc. So as you can see, there are a lot of differences here in these images. So even though we have these differences, still our CNN model recognizes the parrot correctly to its unique features, that is the body color green and the red peak. This happens due to the property called as spatial invariance, which gives CNN flexibility to recognize the image features, even if the object in the image has different lighting orientations, distortion background colors, etc. So now let's see how max pooling works. So let's say we got this feature map after applying convolution operation. Now once we get the feature map, we apply max pooling on it. The way we do it in the first, we define a spatial neighborhood, which is nothing but a 2 by 2 pixel window as shown here. It doesn't have to be necessarily 2 by 2 window, or you can choose any size vector. So you place it on the top or left and take the largest element or value from this feature map within that window and ignore the rest of the 3 elements or values in this case. It is 5 now. Move to the right. Here we have selected the strides of 2. So we should be here now and repeat the same process for other parts too. By doing this, we are still preserving the features. Apparently, max pooling helps extracting the sharpest features of the image. So given an image, the sharpest features are the best lower level representation of an. We know that these largest values are the places where you find the closest similarity of the features. Let's say about parrot has these red beak, which is the feature represented by 8 now. If I rotate this image to change the orientation, I would get the number 8 shifted to this place now. Since it's maximum of the value, I would still be able to capture the feature, which is red beak of the parrot. So we are still able to preserve the feature. By applying max pooling, we are reducing the dimensionality of each feature map, thereby getting rid of features 3 out of 4 pixels, which are not important and hence reducing the size of image. In a nutshell, In a nutshell, we are not only preserving these features, introducing spatial inference, but also reducing the size. Size reduction has seen faster processing during model training, or in other words, speeding up the computations, and also by removing some noise in the data and extracting only significant or important features. We can reduce overfitting in these cases.
Hello everybody, myself Ganesh Ranjan Chauhan, roll number B21047. I am going to present the presentation on the topics fully connected layer, YOLO, and ResNet. So basically I will be starting with fully connected layer. So what is fully connected layer? So fully connected layer is a dense network of neural networks between every two layer. We use fully connected layer to classify the image to a particular category. Like there are many categories present, so we need to specify it to a single category. So it with the help of fully connected layer we do this. So basically after convolution there are many layers formed. So what do we do? Like there are many outputs, so we actually arrange them into a 1D figure, and after the it is converted to a 1D figure, we put it as an input for the next FC layer. So what it does, like after processing it to several FC layers, output is formed. So output have some number of neurons. So basically what it is, the number of neurons in the final like FC layer is equal to the number of categories present. So here are some of the impressive examples of the CNN architecture: LXNet, GoogleNet, JFNet, LENet, ResNet. So moving on to the next topic, we have ResNet. So what is the use of ResNet in our program? So ResNet is, what is ResNet? We need to ask about this now. So ResNet is an artificial neural network that introduced a so-called identity shortcut connection. Like it can skip one or two layers or many, even thousands of layers it can skip and without affecting the performance of the program. So what we used here, we used ImageNet. So ImageNet is actually a large visual database. So it all like like we just import weights from it. So it is already pre-trained data. So what it does, like we import the weights. If we are training the data, we will train it on a 700 or 800, something like that. So what it does, it trains over thousands or lakhs of data, and we just pick up the weights, and with the help of epochs, we just make that data which can be usable by our codes. So like we are using the buildings of the South Campus, North Campus, and Mandi. So we train it according to that, and it can be converted according to our data. So it is the use of ImageNet. So here I will conclude ResNet. So now, okay, so now let us get down to the code.
So as we have three classes in our like classification: South Campus, North Campus, and Mandi. So I'll open South Campus. So these are the photos in it. Here's the North Campus, all photos in it. And now I will show the categorized folders. That is North Campus. It has all the categories in it, like all subfolders in it. So hello everyone, myself Krishna, and my roll number is B1054, and I'll be taking up the code for classifier. So we have imported libraries, some libraries, NumPy, Pandas, and we have used some classes, TensorFlow, Keras. So TensorFlow, Keras have important functions, so like max pooling, global averaging, 2D. So these functions are used for CNN classification. And here we are mounting the dataset into our code. So that's the link. And here we have defined the image width and height. So this is basically the resolution of our images. And every pixel has three colors in it: red, green, and blue. So here we have defined it. So and here we are doing pre-processing of our dataset. So basically, we are rescaling it, and we are splitting our data into training dataset and testing dataset. So 80% is a training set and 20% is a testing set. So these are the number of images in that. So and we have also taken the batch size is 32. It's a standard. And for our satisfaction, we just wanted to see if dataset is good. So we printed it, and we took 25 images from all the three classes: South, North, and Mandi. So here comes the CNN part. So what we did is, like, we imported the weights. We use the weights from ImageNet. So it has predefined weights in it, and we modified those weights according to our dataset. So here's the thing. And now here we firstly used this sequential from Keras to we did batch normalization, and then we did global averaging, and then for the neural network we took 512 neurons as our first hidden layer, and then we used ReLU activation function. So what ReLU does is it results into a value from 0 to 1. So in our second layer, hidden layer, we used 256 neurons, and then we dropped some images, 50% of images, so that overfitting doesn't occur. And the last layer has 128 neurons in it, and the last like the final, we have to classify it into three classes. So here is a final layer, and for final layer we have used softmax. So it is, we can also use sigmoid here. So here we have like printed our model summary, and okay, so here we are running the epoch cycles. Basically, what we're doing is we're training our data set 15 times. So at each step, each step has some accuracy and loss related to it. So after each epoch cycle, the accuracy increases. So here we can see the final accuracy is 0.903, that is 93%, and final loss is this. So now here we have plotted training accuracy and validation accuracy with epoch cycle. So we can say that training accuracy becomes constant after certain epoch, and here we can see that training loss decreases after epoch. So that was our goal, to decrease the training loss and increase the training accuracy. So here we are visualizing the accuracy. So here, for the validation, we can see the accuracy score here, and we have, for our satisfaction, we took an image to like classify it. So
we code in such a manner that uh, zero is Mandi, one is North Campus, and two is South Campus. So the resultant for the after classification, we get the value as one. So this image belongs to North Campus.
What is YOLO V4? Let us know a detailed breakdown of it. So what YOLO stand for, you only look once. So YOLO V4 is the fourth generation of you only look once. So what it is actually? So it is an object detection model as it trains the images and search for the subset of the object classes. So moving on further, let us see what is YOLO V4, how YOLO V4 works, and the significant features of YOLO V4. It will be presented by my next team members.
Hey, this is Raju Sharma. Now, we can clearly see the YOLO V4 is the fourth generation of only look once family of model, and all the YOLO models are object detection models. Normally, YOLO model uses COCO as the dataset, but here we use our custom dataset. So, moving on to the next slide. So, here first we need to know what is backbone. And now, what is backbone? So, backbone is the deep learning architecture that basically acts as a feature extractor. Now, moving on to the next part. So, next is the subset of the bag of spatials. It basically collects feature maps from different stages of backbone. After this, we go to the head part. Now, head is also known as object detector. Basically, after this, we go to the head part. Now, head is also known as object detector. Basically, finds the region where the object might be present, but doesn't tell about which object is present in that region. Now, let's move forward. So, before starting this, we need to know what is self-adversarial training, as known as SAT. We know that DL performs super bad with adversarial data, and thus YOLO V4 uses SAT such that it introduces the X amount of disturbance to the training data till the predicted label remains the same as the original class. This helps the model to become more generalized. Now, looking at this figure. So, what is CSP? CSP is cross-stage partial connection. So now, as the number of layer grows, the last layer have a lesser and lesser context of the feature learned in the initial layers. In order to solve that, researcher introduced the idea of skip connection, such that the gradient can backpropagate to the initial layer with relative ease. DevNet was one such network that has skip connection from every layer to another. So now moving forward to SPP layer. So now YOLO V4 uses an SPP block after CSP darknet 53 to increase the receptive. So now YOLO V4 uses an SPP block after CSP darknet 53 to increase the receptive field and separate out the most important features from the backbone. Spatial pyramid pooling is that we take an input image and use convolutional layer to extract its feature map. Okay, now moving forward to the PN part. YOLO V4 uses PanNet for the feature aggregation of the network. PanNet is basically a feature pyramid network that extracts important feature from the backbone classifier. It uses SPP to make this FPN possible. Now, the next slide will be carried forward by Athar.
So let's move on. Now we have been discussing on YOLO V4 architecture selection. Now, as we have seen, there are a lot of possibilities in choosing architecture. So what exactly do we look for while choosing the architecture? Selection criteria is basically based on the optimal balance between the input network resolution, number of foundation layers, number of parameters, and number of output layers, etc. We are moreover like selection criteria will also be based on the FPS, etc. So in the model which we have used, we have used CSP darknet 53 as a backbone. This is because CSP darknet has more efficient and higher FPS than the rest. Thus, we are choosing the following. Now let's move on to the coding part. So now let's get down to the YOLO code. In the first part, we are mounting a drive to the Google Colab. Next part, we are giving this complete address content G drive, my drive to my drive, which is basically every time we have to use address, we can just write my drive. Now we are entering. I have made a folder YOLO V4 PyFold in my drive, and I'll show it later. We are basically changing directly to YOLO V4 PyFold folder and downloading the darknet to that folder. Now what we are changing, there is a makefile in darknet. Now what we are doing, we are using OpenCV, so it is basically giving OpenCV, which is 0, means it is not operating, to operating. Like we have to make OpenCV of makefile not operating to operating. The GPU from 0 to 1, COD and then from 0 to 1. OpenMP from 0 to 1. These are things we need to use from the makefile. Thus we convert them from 0 to 1 like we are using them. And now this make command basically initializes the above statements and does the work of the above statements here. Like in this statement, the GPU from 0 is converted to GPU to 1. And this is a make command which executes. Now basically we are downloading here the YOLO weights, which are basically darknet. We are downloading the pretrained weights from darknet, which are YOLO V3 optimal weights, like it is being said, like YOLO V4 weights.1. And here we are changing the permission of darknet. Basically darknet does not allow anyone to train data unless permissions are changed. So we are changing the permissions of a darknet folder. And then here I have just installed here we have just installed a library from Git, which helps us in the modeling process. Again, we are going to the YOLO V4 Py folder, darknet folder, and then data. Now what we are doing in the data folder, there is a file process.py. Now what process.py does, let me just show you. Doing the data folder, there is a file process.py. Now what process.py does, let me just show you. So here is a process.py file. Basically what process.py file does, it's first imports globe, OS, numpy, and ss. What it does, it first takes the current directory from where we have to take the images. Then it split the history, like we have to like 10% data we want to test side and 20% data gets to the contain side. Now we use a counter 1, and then again we are using path and file name glob.iglob, which basically transverses to all the images, and then counter.where it randomizes the images and send it to the text and train file respectively. Now file train.close and file val.close basically closes the files and saves the data in the required files. So for example, here we have train.txt file and test.txt file, which is a file which is an outcome of process.py. Now we are basically going on darknet and the CFG folder. Now here is an important part. What the CFG folder contains is a configuration file which tells how our object are gonna make, our model is gonna run. So this is our custom file 12 here. The numbers are changed to class equals to 18, and these are changes we have made in the custom.cfg file. And further we can make changes by using SED command by Google Colab as well. And now after all the changes are made, we are ready to train our data. Now before we train our data, let me just show you so here is the data which contains of image files and the respective annotated annotated text files in a proper YOLO V4 format. And what we mean by annotated text files is, like, first we are using bbox tool to annotate images in a normal form. Like it has like this is a text file which bbox tool gives our output. So bbox tool gives output like width, height, image shape, etc., image size, etc. Now like height, width, image size, and shape, etc. Now the basic command which does not give is the classes to which that particular text file belongs. To do this, we run a convert file which basically converts the text annotated file which we are given to the proper YOLO format like this. Here we are given all the classes which we have. We have classes of A9, A10, 11, A12, A13, OD, director house, guest house, gymkhana, health center, hostels, library, Pine Man, sports, etc. And here we are just converting this to configure the path. We are converting into the particular YOLO v4 format. After we have done so, let me show you how YOLO v4 format looks like. So a proper YOLO, this is a text file which we get out of the convert file. This is the text file converted in a YOLO v4 format. Now, as we have get all our required data, we move on to two folders is py4.names and py4.date. What does py4.names contain? Py4.names contains all the classes which are present in which we are going to detect, and py4.data contains the py4.data basically contains the path of train directory and a test directory, which is my drive YOLO v4 py4 darknet data, and then the train.txt and the test.txt file. And let it open. So we have 18 classes, train data, test data, names, data, py4.names, and we are basically saving the backup folder. Now let's go to a backup folder, which is the third folder which we are using. Now the backup folder basically contains the train weights after each epoch. Like this is the train weight after 1000 epochs. This is the final train weight after 3000 epochs. And now back to a code. This is this we have trained our weights. It is like going region wise and then written the classes in the YOLO format. And now we can see it has done like the 3000. Now we can see the total train data has been done, and it is like now we can see all the training has been done, and now we can test the data. Right. So again, we are going to darknet folder, change the CFG file for other testing data from batch 64 to batch 1 and subdivision 64 to subdivision 1. Next, we go on to a CFG file and test the test data and the main image. So here we have tested our data, foundation layers, and here it shows it okay once it's loaded and the image is being predicted. And here it also shows the number, the percentage, like it is gymkhana 98%, etc. 98%, 72%, 98%, etc. Now here we have designed a function which basically prints out the image in a resize format in a particular format. And here is the IAM show predictions.jpg which basically gives our image. So this is the code for YOLO. And now I'll hand over to Rajiv Sharma to discuss our software part.
So this is our software part. Here's our Python code, and when we run it, here's our HTTP code. Let's copy this and paste it on the Chrome. And here's our front page. So about the front page code, this is our body part, and this is our navigation part, and this is our upload your image part. This is our footer part, and this is our form part. And about the end page, so here's the navigation part, and this is our footer part. This is our background image part, like the body part, and this is our like the end result part. Okay, now let's go to the page and let's upload the file, and here's our result. So we can see is gymkhana.
Hence, we come to the end of our project. This slide shows the contributions done by all our team members. Here, me, Athar Kumar, was majorly in building YOLO model and the coding part. Mohit Singh was involved in concept building and data collection. Nihal Singh was involved in concept building and CNN. Krishna Singh was involved in the code of CNN. Gyanish was involved in CNN and YOLO and PPT design. And Rajiv Sharma was involved in software development and the video work. One thing to note that likewise we have made the YOLO model for South Campus also in case the before image is belonging to the South Campus. Thus we come to the end of our project, and I hope you liked it. Thank you.